Hello, I welcome you all in this presentation related with the subject materials processing fundamentals and practical. In this particular talk, I will be talking about the hot and cold forming or also known as hot and cold working. So, this particular topic is related with the bulk metal deformation based manufacturing process or material processing, wherein large scale plastic deformation is realized through the controlled application of the suitable kind of the stresses, so that the permanent plastic deformation in the raw material is realized to obtain the desired size and shape of the product. So, since this approach is based on the plastic deformation to manufacture a particular product, then material should have a suitable ductility as well as a lower yield strength. Material should have suitable mechanical properties for easy application of bulk metal deformation based manufacturing process. So, in this talk basically I will be focusing on when the bulk, what happens to the metal when the bulk deformation is carried out under the cold conditions, that is in ambient condition, or in hot conditions, that are hot conditions which is above the recrystallization temperature. Okay. So, we will be focusing in this talk primarily on hot forming or hot working, cold forming or cold working. Okay. So, the content of the topic includes the bulk metal forming, what it is and what are the broad category of the processes. Then we will try to focus on the cold and hot forming, like how the things are done, how the metal is affected which is subjected to the hot and cold forming, and the ease of manufacturing by hot or cold forming to process the material by the bulk metal based deformation processes. And then what happens to the metal which is subjected to the cold or hot forming in terms of the microstructure, mechanical properties, the kind of tolerance that is realized or the dimensional control which is possible, then surface finish that is realized, and the power requirement or the force need to be applied for hot or cold metal forming. So, these two category of the hot or cold forming processes or hot or cold working processes are related with the bulk metal forming. So, in bulk metal forming, what is done basically, the force is applied in such a way that the significant plastic deformation of the raw material is achieved to obtain the desired size and shape. And to achieve that the plastic deformation easily, it is necessary that material is having reasonably good ductility and preferably lower yield strength, so that this kind of deformation can be achieved easily. Okay. But many metals may not show the very good ductility, or they may show higher yield strength, which will make the deformation little difficult, and therefore, sometimes heating of the metal to the higher temperature reduces the yield strength and increases the ductility, which in turn facilitates the plastic deformation. So, bulk metal forming is basically a family of the manufacturing processes where large scale plastic deformation is realized. Okay, to large scale plastic deformation of the stock or raw material is realized using suitable kind of the stresses. These may be compressive, these may be tensile, these may be bending type, and when the plastic deformation is realized, that helps in obtaining the product of the desired size and shape. Okay. And but for this the bulk metal forming, material must have good ductility, and it is preferred that it is having the lower yield strength, so that the deformation can be realized using the lesser force, lesser power consumption, and it will be further better if the metal is having the lower work hardening tendency. Otherwise, it will gain the strength and will make the deformation difficult. Okay. And this is particularly preferable if it is having, if the high ductility, low yield strength and low work hardening tendency is available at the room temperature in a metal for easy metal forming. But many times the metals do not show very high ductility or very low yield strength. So, in those cases, metals having the low ductility and high yield strength, then the bulk metal forming for such kind of the metals, the heating is done using the suitable heat source. That heat source can be resistance heating, induction heating, flame, or any other kind of the method which can be used to increase the temperature of the metals. So, when the temperature of the metal is increased, we can see that the yield strength of the metal comes down. So, the drop in yield strength of the metal with the increase of temperature is different for the different metals, like those which show significant thermal softening due to the heating, there will be significant drop in the yield strength. Like say the great drop in the yield strength is observed in aluminum and copper alloys, or aluminum copper alloys like 6000 2000 series aluminum alloys. Carbon steels, the drop is somewhat less, the nickel steels, and then austenitic stainless steel. So, in all the cases there will be drop in yield strength of the metal at a higher with the increase of temperature, but the drop percentage drop may vary with the metal system itself depending upon their thermal softening tendency. Okay. So, when the metal is softened, then its the ductility is usually enhanced with the coupled with the reduction in yield strength, and that in turn facilitates the plastic deformation easily, even in those metals which have the high yield strength and low ductility at room temperature. Okay, so if we see that the bulk metal forming processes, these are the four most common bulk metal forming processes. The rolling is one where the thick section component or thick section stock or the raw material is passed through the two rollers, okay, and that in turn causes the controlled plastic deformation to reduce the thickness. So, in that case thickness is reduced from the T1 to T2 after passing through these rollers like this, okay. Then when it is passed, then it is deformed plastically, and this in turn so this reduction in thickness is coupled with the increase in length. Width usually remains constant. So, the rolling is one process where significant reduction in thickness is realized coupled with the increase in length, while there will be marginal or very little change in the width of the sheet which is being rolled. So, the rolling is one bulk metal forming process. The forging is one another one which can be like the open or close forging. So, what happens, we can apply compressive load for forging purpose, and when the compressive load can be applied in two ways. It can be applied using either manually operated hammers or the power operated hammers. So, that is one. So, the manual hammers or the powered hammers. So, the hammers will be continuously blown over the raw material to get the desired shape, and between the blows of the hammer the metal is manipulated in controlled way to achieve the desired size and shape, okay. And this is one, and the another one is where the material is subjected to the continuously increasing load. So, with the help of suitable press, this kind of the approach is used for controlled plastic deformation of the material. So, in that case what we do, we take one die and the raw material is like this, and what we do, then the load is applied from the top, okay. So, the material will be filling in the cavity and achieve realizing the desired shape. But when the press forging is used, in that case the load is increased gradually until whole of the metal fills the die cavity. As far as the open and close forging is concerned, in case of the open forging, both the dies are open and the metal flows literally, while in case of the closed forging, both the dies will have one upper die and lower die. So, in between we will be putting the raw material to be deformed. So, the upper die will be lowered and the lower die will be kept on the anvil, and this in turn will be, so when the lower die is upper die is moved in controlled way with the help of a suitable press by increasing the magnitude of the pressure continuously, the metal in between the dies is forced to flow plastically, okay. So, that in turn helps in achieving the desired size and shape. So, this is particularly used for making the sheets and plates, while forgings can be used for making the variety of the high strength to weight ratio products, like it may be the wrenches, the even gears, connecting rod. So, these are the typical products which are made by the forging, and a lot of hand tools are also made with the help of the forging approach of the bulk metal forming. Extrusion is particularly used for making the long cylinder raw materials. Okay. So, these are basically uniform section components, whether it is say square, and this will be running in meters. Okay. So, long cylindrical, the raw materials are made using the, or stocks are made using the extrusion process. These can be of the different cross section, it can be circular, it can be any other as per the need. Okay. So, the extrusion is a process which offers the significant great reduction in the cross section in one go. Great reduction in cross section. Initially, the dimension is like this, and when metal is forced to pass through the die, then the reduction can be huge. One pass. So, the metal is forced, so it will be flowing through the die like this. Okay, this is say die. All right. So, this huge drop in cross section is realized by the extrusion, and extrusion is usually hot because of the significant reduction that is realized by the extrusion. So, in if we see in these processes, the significant plastic deformation is involved in shaping the material. Okay. The drying is the another process which can be like drying, it can be used for making the cup shape product, or there is another variant of the drying which is called wire drying. So, wire drying is used for making the bars. Bars are converted in form of the wires with the help of wire drying, and these will be involving the significant plastic deformation to achieve the desired size and shape. So, the point here is there are many bulk metal forming processes, okay, and this bulk metal forming can be done under the cold conditions, that is under the room temperature conditions, or it can be done under the hot conditions, that is greater than the recrystallization temperature. Okay. So, the one which is done at room temperature is called cold forming, and one which is done at a high temperature above the recrystallization temperature is called hot forming. These processes can be done both at rolling, forging, extrusion and drying. These can be done under hot or cold conditions, but certain processes are preferably done under the hot conditions, and few other processes are done in the cold conditions. It is also possible like few stages are done in the hot conditions and other stages are done in cold conditions to achieve the desired structure and properties of the final product. So, we may use a combination of the hot and the cold forming. Okay, what happens when metal is subject? We know that if the metals, most of the metals at room temperature show high strength and lower ductility, but when a metal is heated to the high temperature, okay, strength of the material tends to decrease while ductility increases. So, it indicates that metal becomes less resistance to the external stresses at higher temperature, and it can be deformed easily without breaking, which means if the material is showing greater ductility, then it can be deformed plastically without cracking or fracturing. This is because increased thermal energy allows the atoms to move relatively easily to facilitate the plastic deformation, and this kind of the movement is happens through the like say the deformation mechanisms like slip and twinning. These are the three mechanisms which are attributed to this drop in strength and increase in ductility. One is atomic bond weakening. When the temperature is increased, the atomic bond strength is reduced, and that in turn facilitates the movement relatively easily to facilitate the deformation. Dislocation movement is also accelerated or enhanced at a high temperature, and that in turn reduces the stresses required to cause slip and twinning to facilitate the deformation. Sometimes even the phase change in some of the metals is observed when the metal is heated to the high temperature. Initially, it may be having one crystal structure, one microstructure. When it is heated to the higher temperature, there will be change in the phase structure or crystal structure of the metal, and those changes in turn lead to the reduction in the strength and increase in ductility. So, this is the general trend that we can see. When the temperature is increased, the yield strength comes down and the ductility increases. So, when a metal is subjected to the lower temperature, subjected to say the deformation or the external load at low temperature, then it shows the higher stress. The stress sustained behavior is like this. So, the ultimate stress is high, yield strength will also be high. While when the same metal, when it is heated to the high temperature, the strength comes down and the elongation or the strength at the, which is observed at the time of fracture, that is increased. So, this indicates that materials strength comes down and percentage elongation, that is the strain, which is also known as ductility, that increases with the increase of the temperature. While these may be high at low temperature and elongation will be less, okay, at the low temperature. So, increasing temperature increases the ductility. Most of the materials become more ductile as the temperature rises due to the increased atomic movement, which allows the greater plastic deformation before fracture, that is due to the increased ductility. Increasing temperature decreases the strength due to the weakening of the atomic bond, and the exact relationship between the temperature and the variation in mechanical properties, that depends on the metals. Like it is very much possible, like with the increase of the temperature, then, and here if we see the yield strength, then for one metal the relationship may be like this, and for another metal relationship may be like this. So, here for M1 and M2, one metal softens very rapidly as compared to the other. So, the relationship between the temperature and mechanical properties significantly depend on the metal itself. So, that indicates the thermal softening behavior. There are multiple mechanisms which will be working behind these variation in mechanical properties, like recovery, recrystallization, and the work hardening. About that we will be talking in the next lecture in detail. Another way by which the mechanical properties which are affected by the temperature is the ductile to brittle transition temperature. So, about this we have also talked last time, like if we have the temperature in the x-axis and the toughness in the y-axis, then at high temperature material showing the high ductility, at lower temperature high ductility and high toughness, at lower temperature its toughness drops like anything. So, this temperature at which this drop takes place, significant drop in toughness takes place, that is known as ductile to brittle transition temperature. So, when there is a drop in temperature of the metal, most of the metals tend to become more brittle, which means at lower temperatures, with a drop in temperature, even if you go in the sub-zero conditions, there will be increase in yield strength and drop in percentage elongation, drop in and the toughness value. This is what happens with the reduction in temperature. Okay, so if this kind of the variation is taking place, then material behave like a brittle material. Okay, but as far as the cold metal forming and hot metal forming is concerned, for hot metal forming we have to heat the metal, so the temperature is enhanced, that in turn will be increasing the ductility and reducing the strength to facilitate the plastic deformation. At the same time, the work hardening tendency at a higher temperature is also minimized due to the continuous recovery and the recrystallization that will be happening at a high temperature during the deformation itself. So, the work hardening tendency of the metal is minimized at a higher temperature, that also facilitates the significant plastic deformation of the metals without cracking tendency at a higher temperature. So, these are the mechanisms as I have said in summary in the previous slides. So, the atomic movement is one which is contributing towards the drop in yield strength and increase in ductility. At a higher temperature, atoms within the material have more kinetic energy and can move rapidly past over each other and enabling the plastic deformation without causing fracture. The another one is dislocation movement. Increased temperature facilitates the movement of dislocations by like climb up, climb down, and the annihilation of the dislocations, softening of the metal. So these crystallographic defects, you see, so these dislocation, once the dislocation movement is facilitated, then this will be facilitating the plastic deformation easily. Okay, and the phase change in some materials, the phase change or the transformation of certain phases at elevated temperature also lowers the strength. Say, so that happens in multiple metals systems where the change in the crystal structure from BCC to FCC it happens, or change in phase from alpha iron to the gamma iron. So, there will be the multiple kind of the phase changes which can occur at a higher temperature. Even few precipitates at low temperature may be present and they may get dissolve at a higher temperature. So, these in turn will be reducing the yield strength and facilitating the deformation without cracking or fracture tendency. Now, we will talk about the conditions which are primarily used to distinguish the hot and cold forming to realize the plastic deformation and make the products. Bulk metal forming processes which are done at room temperature or below the recrystallization temperature of the metal are called cold forming, while the bulk metal forming process which are executed above the recrystallization temperature are called hot forming. So, if we see this schematic diagram, say this is the x axis showing the forming temperature, and in y axis we have just like say the classification of the process. So, and this is the recrystallization temperature of the metal. So, when the plastic deformation of the metal is realized above the recrystallization temperature, we categorize the processes, bulk metal forming process, as a hot forming, and when the processes are done at room temperature it is cold forming, and in between the room temperature and the below recrystallization temperature it is termed as warm forming. So, the forming process is performed between the room temperature and the recrystallization temperature called warm forming. Okay. So, what happens when the hot forming is carried out? When the metal is heated above the recrystallization temperature, it facilitates the recovery and recrystallization during the deformation itself. That is called dynamic recovery and dynamic recrystallization, and which in turn lowers the yield strength and work hardening tendency besides increasing the ductility. Okay, and because of this reduction in yield strength, reduction in work hardening tendency, increase in ductility, our ease of forming process is enhanced with the increasing temperature. And since the soft material has got soft and ductility is enhanced, so it requires lesser stress, lesser force to facilitate the plastic deformation, and that in turn reduces the force or the power required to cause the hot forming. Okay. So, the force and power consumption for hot forming is found to be much lower than the cold forming, and this is particularly attributed to the drop in yield strength and a decrease in the work hardening tendency of the metal itself. So, absence of work hardening of the metal during the hot forming allows the continuous and significant plastic deformation without having the cracking tendency. So, this is the good part of the hot forming, but there are many challenges also in the hot forming. So, when the hot forming is done, metal will be heated to the high temperatures, and if it is being done under the ambient conditions, then metal will react with the ambient gases like oxygen and nitrogen, and the oxide and nitrites will be formed at the surface. So, the formation of these oxides and nitrites at the surface, that will be leading to the drop in surface roughness, drop in surface finish, or increase in surface roughness, and this will also be leading to the little loss of the material in form of chipping of these oxides and nitrites which are being formed. So, the hot metal forming offers many challenges in the form of oxidation tendency of the metal, resulting in relatively higher surface roughness coupled with the metal loss, because these oxides will subsequently be chipped off from the surfaces during the either during the forming or during the post cleaning action. Another thing is that when the metal is heated, so obviously due to the as per the thermal expansion behavior, its dimensions will enhanced, okay, like this. So, it will expand in all directions, and in expanded position it will be subjected to the plastic deformation. So, say particular shape has been given after the plastic deformation at a high temperature when it is hot. Now, when it is subjected to the cooling during the, you see, after processing it will be cooled. So, again due to the contraction there will be reduction in the dimensions. So, this expansion, the plastic deformation which is permanent, is being carried out at a higher temperature, but later on when the metal is cooled or the semi processed product is cooled or finished product is cooled, there will be shrinkage, and that shrinkage will be again leading to the change in dimensions. So, this expansion coupled with the shrinkage leads to the poor control or limited control over the dimensions of the raw material or the product or semi finished product which is being made by the hot forming. So, thermal expansion and contraction of the metal during or after the bulk metal hot forming process makes it difficult to realize the desired dimensional accuracy and tolerance. So, the key issue here is the desired shape and size in a metal under hot working condition is realized at high temperature. After giving the desired size and shape at a high temperature, when metal cools down, it experiences shrinkage, and that shrinkage or that contraction leads to the change in dimensions. If the, especially if the product is having a different dimensions in the different sections, then that will make the job of the dimensional control further difficult, and that is why what we see when we increase the forming temperature, then dimensional accuracy is compromised, dimensional accuracy is reduced, while the surface roughness is enhanced. So, enhanced surface roughness is attributed to the formation of oxides and nitrides, and drop in dimensional accuracy is attributed to the significant expansion and contraction that will be taking place during the hot forming process. Cold forming on the other hand is carried out at a room temperature. So, at room temperature, since the metals have the greater yield strength, so it offers the greater resistance to the plastic deformation due to the higher yield strength and lower ductility. Therefore, cold forming needs stronger and more robust machines so that the heavy force can be applied to facilitate the plastic deformation. Okay. Therefore, it needs greater force and power consumption for bulk metal forming. So, the cold metal forming has to handle the metals of higher yield strength at a room temperature as compared to that of the hot forming for the same metal, and therefore, it needs the more robust machines, greater force and greater power consumption for cold metal forming. Okay. Further, the cold metal forming, since the metal is not heated to the high temperature, so the tendency for oxidation is very limited, and therefore, we get very good surface finish, and there is no expansion and contraction like hot forming. So, we get very close control over the dimensions and the tolerance due to the absence of oxidation and thermal expansion and contraction possibilities. So, if we see cold forming, extent of deformation that can be realized in cold forming, that is limited, because materials do not have, metal at room temperature does not have that much ductility. So, it will tend to show the work hardening, increase in yield strength, decrease in ductility, and if the metal is subjected to the significant plastic deformation during the cold forming, then it will show the cracking tendency. Okay. So, under the cold forming conditions, when the plastic deformation takes place, so there will be work hardening, which in turn will be leading to the increase in yield strength and drop in percentage elongation. So, ductility is coming down and yield strength is increasing, which will make the cold forming in later stages difficult. Okay. So, and when the drop in ductility is significant, then it can increase the cracking tendency. Okay. So, it may be required to eliminate this, the embrittling effect being induced due to the work hardening, and for that we may have to do the process annealing. Okay. This process annealing will be relieving the work hardening effect or inducing the ductility for further cold forming process. Okay. So, the extent of deformation, because the yield strength is high, ductility is limited. So, limited deformation is possible during the cold forming, that is the first thing And when the metal is subjected to the cold forming, then it causes the work hardening and increased cracking tendency due to the drop in ductility and increase in yield strength. And this process is also limited by the system capabilities. You see, if the material is having too high yield strength, then it may be very difficult to facilitate the plastic deformation under the room temperature conditions, and so it may also be limited by the system capabilities. So these are, you can say, little negative aspects as far as the cold forming is concerned. Material subjected to the work hardening, which increases the yield strength and ductility, makes the deformation difficult, and it requires very high forces to facilitate the plastic deformation. Okay. So that's what we can see here. When the plastic deformation is carried out, so there will be increase in plastic strain, and that will be causing the increased hardness and yield strength continuously. Under the hot conditions, the work hardening is very limited or it is absent. So this curve usually remains flat, and there is no major significant increase in yield strength and the hardness. So partially deformed metal during the cold forming is therefore subjected to the annealing, that's process annealing, to remove the work hardening effect and induce the ductility. If this is not done, then it will start showing the cracks in later stages of the cold forming. Process annealing allows further cold forming of the metal, otherwise surface cracks of the cold formed component can start. Cold forming of the soft, ductile, low yield strength, low hardening metal is relatively easy. So like aluminum, magnesium, zinc, and even mild steel. So these are relatively soft, not mild steel, but aluminum, magnesium, and the zinc are relatively soft. So when the metal is soft, ductile, and of low yield strength, showing the lower work hardening tendency, then these can be easily processed by the cold forming process to get the desired size and shape without requirement of the external heating. Okay. So this is one aspect. The soft, low yield strength and ductile metals can be subjected to the cold forming easily to get the desired size and shape, while the high yield strength metals and low ductility metals having the high work hardening tendency, like high strength steels, cobalt alloys, nickel alloys, these are generally processed by the hot forming because they will show a great resistance to the plastic deformation coupled with the increased cracking tendency. Now we will see that how the two hot or cold forming processes can be compared with regard to their capabilities and the performance. When cold forming is done at temperature less than the recrystallization temperature, which is usually, let's say, less than zero point 0.3 times of the melting point, cold forming requires higher force and the power because of the high yield strength and limited ductility. Cold forming shows the strain hardening tendency, and that in turn increases the yield strength, makes the continuous and further cold forming in later stages difficult. Absence of oxidation and nitride formation at the surface during cold forming results in the good surface finish, and absence of the heat change in dimensions due to the heating and cooling, thermal expansion and contraction, that is absent in cold forming. So that in turn results in the good dimensional control and the lower cost of the process and equipment, because it does not require the systems for handling the hot metals, heating the hot metals, and related the process controls. When the cold forming is done, residual stresses develop at the surface, and since the temperature is not much, so there is no recrystallization, but the deformed metal shows the elongated grains. Initially the metal may have equaxed grains, but after the deformation it may show the elongated grains. And the last point is this where less deformation is possible in one pass or in one go during the cold forming, because the metal shows higher yield strength and lower ductility at a low room temperature, and therefore relatively less plastic deformation is possible, less reduction or less change in dimensions is possible at the room temperature during the cold forming as compared to the hot forming. So if we compare these aspects with respect to the hot forming is carried out at a temperature greater than the recrystallization temperature, which is say point greater than the 0.5 times of the melting point. Because of reduction in yield strength and increase in ductility, lesser force or power is required. Strain hardening effect is absent at a high temperature above the recrystallization temperature, because there will be work hardening, and the recovery and recrystallization continuously will be leading to the absence of the strain hardening effect. There is a huge tendency of oxide and nitride formation at the surfaces to the heating of the metal and ambient conditions, so that spoils the surface finish. Due to the thermal expansion and contraction, due to the heating and cooling experience during the hot forming, the limited dimensional control is possible during the hot forming. Since we have to have the systems for heating and handling the material at a higher temperature, so the process cost of the higher process cost and the equipments. Since the metal is heat, deformation is carried out when the metal is hot at a higher temperature, so there is no residual stress development, and the recrystallization and recovery are the dominant mechanisms which will be happening due to the high temperature. And the grain structure which is distorted during the deformation is again recrystallized, so we get usually fine and waxed grains. And a significant reduction in yield strength and increase in ductility facilitates the greater reduction in or greater deformation in one pass of the metal. So now here I will summarize this presentation. In this presentation, basically I have talked about the bulk metal forming process approach and the importance of the hot or cold metal forming, and how do they affect the material characteristics and the process capabilities of the bulk metal forming process. Thank you for your attention.